And dear students, in the previous videos, we have discussed about the our unit 1, that is introduction to energy audit. So in that we discussed about the various what is meant by energy conservation and what is meant by energy efficiency and what are the various energy conservation schemes and what are the various acts proposed by our government and what is meant by the energy conservation act and what is meant by energy audit and what are the different types of the energy audits, that means preliminary energy audit and detailed energy audit, and what are the various diagrams, that means Sankey diagrams and load profile diagrams and pie charts, and what is meant by cost index and what is meant by the energy index, and what are the BWE standards, like that. So in this video onwards we will see about the our unit 2, energy efficient motors and power factor improvements. So what are the contents present in the our unit 2 is first energy efficient motors. So in this we will discuss about the factors affecting the efficiency, loss distribution and construction details, characteristics and variable speed, variable duty system, cycle systems, and RMS HP, and voltage variation, voltage unbalance, over motoring, and motor energy audit. And second part is power factor, methods of improvement of power factor, and power factor with non-linear loads. So in this video, I want to discuss about the factors affecting the energy efficiency and loss distribution and construction details with 3 PPTs. So let us move to our discussion. So what are the factors affecting the energy efficiency means here mainly 8 factors are there. So what are the 8 factors? First one is losses. So to reduce these losses, what we do? Use energy efficient motors. And what is the second factor? Underloading. So to overcome this underloading, we can go for the avoid the oversized motors. And third one is the size to variable load. So prefer the RMS HP motors. And power quality. Fourth one, comply with the standards set by the BIS in voltage variation and unbalance. And fifth factor is rewinding. So replace with new energy efficient motors. That is a remedy for this problem. And poor power factor, use the power factor correction by using the capacitors. And inadequate maintenance, enhance it. And age effect. So these are the factors affecting the energy efficiency of motors. So energy efficiency opportunities. So first one, use of energy efficient motors. That means for what purpose? For reducing the losses. So what are the various types of losses in our motors means? So normally in the most of the cases, domestic purposes or any purposes, we use induction motors. So that's why we discussed completely about the induction motors only. So what are the various types of losses? Fixed losses and variable losses. So what is the fixed losses means? In the stator we have the iron. So the losses present in the stator is called as the friction losses, and the losses come in the copper. Copper materials are known as the copper losses. So the fixed losses, use of how we can improve these fixed losses means use of the thinner gauge. Thinner gauge. So what are the fixed losses means? In the core side losses are called as the fixed losses, and the core losses are further classified into 2 types: eddy current losses and hysteresis losses. And eddy current losses means because of the magnetic reversals of the dipoles or domains in the magnetic material, the losses will be occurs. Those losses are nothing but hysteresis losses. And eddy current losses means because of the large area of the core, some circulating currents are flow inside the magnetic material. So because of that circulating currents, some losses will be there. Those losses are nothing but eddy current losses. So to reduce these eddy current losses and hysteresis losses, what we do means for hysteresis losses we can provide the high permeable material, and for eddy current losses we can provide the laminations. And similarly we have the copper losses which are called as variable losses. So the copper losses are classified into 2 types. What are those 2 types means? In the stator we have winding and in the rotor we have winding. So in the stator winding we have the stator copper losses, And in the rotor we have winding, those we are called as the rotor copper losses. So in the stator copper losses, use of more copper and large conductors increases the cross sectional area of the stator windings. This lower resistance of the windings and reduces the losses due to the current flow. And similarly, in the rotor iron losses, rotor copper losses, use of the large rotor conductors bars increases the size of the cross section and lowering the conductor resistance and losses due to the conductor current flow. And in addition to the fixed losses and variable losses, some other losses is also there. Those are nothing but frictional and winding losses and stereo load losses. So what are the efficiency improvement in this point of view are in the friction and winding losses, use of low loss fan design reduces the losses due to the air movement, and stray load losses, use of the optimizer design and strict quality control procedures minimizes the stray load losses. And second point or second opportunity, reduce underloading. So what are the reasons for the underloading are large safety factor when selecting motor, underutilization of the equipment, and high starting torque is required. And consequences of the underloading are increased motor losses and reduced motor efficiency and reduce the power factor also. So replace with smaller motor. To reduce the underloading, we can replace the oversized motor with the help of a smaller motor if motor operates at less than 50% operations. And next, the third opportunity in the energy efficiency is sizing of the variable load. So motor selection based on highest anticipated load is very expensive and risk of underloading, so we cannot prefer this one. And slightly lower than the highest load and occasionally overloading for short periods, this is very considerable for the variable loading systems. So motors have service factor of 50% above rated load for this case, which case slightly lower than highest load, occasional overloading for short periods. So but avoid the risk of overheating due to extreme load changes and frequent or long periods of the overloading and inability of motor to cool down. And the fourth point, our fourth opportunity for the energy efficiency is improve the power quality. So motor performance affected by the poor power quality. So too high fluctuations in the voltage and frequency, and voltage unbalance. So unequal voltages to three phases of motor. So for example, here we have example 1 and example 2 and example 3. So for the example 1, the voltage unbalance is 0.30% and unbalance in the current is 0.4% and temperature increase is 0%. And for example 2, the voltage unbalance is 2.30% and the unbalance in the current is 17.7% and temperature increase is 30%. And similarly for the example 3, the voltage unbalance is 5.40% and the unbalance in current is 40% and the temperature increase is 40%. So among these three, which one is most efficient one is means example 1 is the most efficient one. And similarly, to keep the voltage unbalanced within the 1% only. So balance single phase loads equally among the three phases and segregate the single phase loads and the feed them into separate lines or transformers. This is the technique to improve the power quality. And rewinding. So rewinding, sometimes 50% of motors can reduce the motor efficiency. So maintain efficiency after rewinding by using the qualified or certified firm or maintaining original motor design or replace 40 HP greater than the 50-year-old motors instead of the rewinding. So sometimes it is better to go for the buying of the new motor instead of rewinding. Why? Because if you, even though we rewinding, that may not be useful for the efficient operation. And improve the power factor. So the power factor can be improved by using the capacitors for induction motors. And benefits of the improved power factor is reduced kVA and reduced losses and improved voltage regulation and increase the efficiency of the plant electrical system. So capacitor size not greater than the 90% of the no load kVAr of the motor. Next, the seventh point is maintenance. So checklist to maintaining the motor efficiency. So inspect motors regularly for wear and dust or dust, and checking motor loads for over or underloading and lubricants as applied properly or not, and check alignment of motor and equipment and ensure supply wiring and terminal box and properly sized and installed and provide the adequate ventilation. So age is also one of the main factor for influencing the energy efficiency. So age causes the deterioration in the motor efficiency over time, which might be due to poor maintenance. So these are the various factors affecting the motor efficiency. Various factors affecting the motor efficiency. So next, the second one is the loss distribution. That means for a same output electrical motor, that means 10 horsepower electrical motor, if you consider two different ranges, that means one is for 81% efficiency and another is for 88% efficiency. So suppose if you consider the 81% efficiency, then output by input is equal to input electrical power is equal to, we know that efficiency is equal to output by input. So then input is equal to output by efficiency. So here the output is 10 horsepower, that means 10 into 746 watts by 0.81. Then the input power is equal to 9210 watts, 9210 watts. And similarly, losses is equal to input minus output. So input is here 9210 and output is 7460. So if you subtract, then we can get the losses 1750 watts. And similarly, if you consider the 88% efficiency motor, then the losses are 1017 watts. So where we can get the less losses in the 88% of the efficiency. So as we prefer more efficient motors, as we prefer more efficient motors, then the loss distribution is less in those motors. So power stages in an induction motor. So power input motor through the stator. So the losses will be classified into stator copper losses and iron losses, and the rotor input losses. So the rotor input losses again classified into rotor copper losses and mechanical power losses developed. So that mechanical power losses will is nothing but the rotor output or motor output. So loss distribution. The different types of losses that occur in the motor are, I already discussed in the previous discussion. Power losses. Power losses are nothing but the stator copper losses and core losses. Sorry, copper losses. Core losses. Core losses are those found in the stator and rotor magnetic field. And friction and windage losses, bearing friction and windage and circulating air through the motor. And stray load losses. These losses are very according to square of the load currents and caused by the leakage flux induced by the load currents in the laminations. So within a limited range, the various motor losses are independent of the each other. So for a motor, the what are the percentage of the losses in the motor components are, the stator power losses are nearly 37%, and the rotor copper losses are nearly 18%, and the magnetically core losses are nearly 20%, and friction windage losses are nearly 9%, and the stray load losses are nearly 16%. And next, typical loss distribution for the NEMA, National Electrical Manufacturers Association design B and design A. So these are the parameters for the single horsepower, 1 horsepower, and these are the parameters for the 5 horsepower, and those percentage of losses and the amount of losses. So when compared to those losses, the efficiency will be, for a single horsepower, the efficiency is 73, and the 5 HP, the efficiency is 83, and losses also less in the 83 per the 5 horsepower, and the losses are also less in the single horsepower. That means as the horsepower increases, the efficiency will be increases. So for increasing of 1% efficiency for various horsepowers, so how the losses will be decreases. So this the table will be represents. So for single horsepower, suppose the efficiency will increases from 73 to 74, then 8% of the reduction of the losses. And if you consider the horsepower, 5 horsepower, 5 HP, then the efficiency increasing for 83 to 84, then the losses will be decreases to 11%. And like that, for efficiency 200 horsepower, the efficiency increases from 93 to 94, then the losses will be decreases to 38%. So conclusion, what is the conclusion? As we prefer the energy efficiency motors, the loss distribution is very low, and as we prefer the horsepower motors, high horsepower motors, then also the loss distribution is less. That means to get the lower loss distribution, we prefer for the high efficiency motors and high horsepower motors. And this is the how the efficiency is improved. So how efficiency is improved? Reduction in the iron losses and reduction in the copper losses. So to reduce the iron losses, what we do? We can provide the high permeable material and reduce the eddy current losses that by providing the laminations. And to reducing the high copper losses, what we do? We can use the more number of tons. More number of tons. That means core length has to be increased to maintain the starting torque. And energy losses. So what are the various losses? We already discussed in the previous discussions. Rotor losses. Nearly those are present in the 20%. So heating in the rotor winding can be reduced by the increasing the size of the conductive bars and end rings to produce the lower resistance. And similarly iron losses 23%. So energy required, the iron losses are for both armature core and the stator core. So energy required to overcome opposition to the changing magnetic fields in the core material, so can be decreased by using the better quality steel and by lengthening the core to reduce the magnetic flux density. And energy losses, windage and friction losses, air resistance and bearing friction are essentially independent of the motor load and can be reduced by improving bearing and seal selection, airflow and fan design. Energy efficient motors produce the heat and use a smaller fan. And stereo losses 9%. The result of the leakage fluxes induced by load currents can be improved by improving the slot geometry. And construction, it consisting of the same construction, which is all the windings are divided into 120 degrees phase displacements, and it is a consisting of a steel frame that supports a hollow cylindrical core and core constructed from the staked laminations and having a number of evenly spaced slots providing the space for the stator winding. And construction, a revolving rotor are also there. The revolving rotor will be classified into two types: squirrel cage rotor and wound rotor. So squirrel cage rotor conducting bars laid into the slots and sorted at both ends of the sorting links. And the wound rotor complete set of the three phase windings exactly as the stator and usually star connected at the ends of the three phase rotors wires and connected to the three slip rings on the rotor shaft. In this way the rotor circuit is accessible. So here how the squirrel cage rotor is there and how the slip ring rotor is there, we have in the diagram. And the last distributions already we have in the previous discussion. And special design features, higher efficiencies are achieved by following special features. What are those special features? Low loss special grade of thinner laminations, this reduces the iron losses even at partial loads. And thicker conductors and more copper contents reduce the copper loss due to the lower resistance. And longer core length reduced the uniform air gap between the stator and rotor to reduce the stay load losses. And special design of fan and fan cover to reduce the windage losses. So first one is the stator winding. Increased the mass of stator winding and rotor and earth rings. Mass of the rotor conductors are increases and air gap, narrowing the air gap. And laminations, thinner laminations of the higher quality steel. And bearings and fans, low loss fan design and quality bearings. So comparison of the hybrid electrical motors when compared with the standard motors. So the hybrid electrical motors have the loss components of 1170 and hybrid electrical motors have 765. So most typically used motor is which motor? Hybrid electrical motor, that is design motor B for 10 horsepower. So this is about the construction details of the energy efficient motor. Thank you.